Imagine you're trying to assemble a massive jigsaw puzzle, like a 10,000-piece puzzle.
Okay, sounds exhausting already.
Right. But there's a huge catch. You're only allowed to hold one puzzle piece in your hand at a time.
Oh, wow.
Yeah. And every single time you pick up a new piece, the rules dictate that you have to scan your eyes over every single piece you've already placed on the board.
One by one.
Exactly. One by one, before you can figure out where the new piece goes. At the start, it's pretty easy. But by piece 5,000, you're spending hours just reviewing the board for a single move.
Which is incredibly inefficient.
Completely. And this is actually the fundamental bottleneck of modern artificial intelligence. I mean, the models are getting smarter, but they're trapped by a memory system that essentially forces them to constantly reread their own past thoughts.
Yeah, and it consumes massive amounts of electricity. It requires literal warehouses full of processors. And honestly, it really limits who gets to build the future of AI. Because the field has largely just accepted this inefficiency as the cost of doing business, the prevailing narrative out there is, well, if you want a smarter model, you just throw more supercomputers at the problem.
Right. Just brute force it.
Exactly. We treat intelligence as a brute force scaling issue, completely ignoring that the underlying mechanism for memory might just be fundamentally flawed.
Which brings us to the mission for today's deep dive.
Yeah.
We are looking at a foundational paper that challenges that exact narrative. It's titled Nautile-370M, Spectral Memory Meets Attention in a Small Reasoning Model by Trickster, Makes and Chinabo.
It's a fascinating read.
It really is. We're going to explore how a team basically ripped out the standard AI memory system, replaced it with this radical mathematical concept, and managed to build a hyper-competent AI model using hardware you could practically plug into a wall outlet in your garage.
Yeah, and just for context on the scale here, the model we are discussing today has just 371 million parameters.
Which sounds like a lot, but
But the models most people use daily are operating with hundreds of billions of parameters. And this tiny model was pre-trained on a single Google TPU V464 slice for exactly 30 days.
which is an almost absurdly small compute budget.
It's practically nothing in this industry, yet it manages to outperform significantly larger models from major tech companies.
So to understand how a 371 million parameter model achieves that, we have to look back at that jigsaw puzzle problem I mentioned earlier. Because the vast majority of major language models are based on the transformer architecture,
Right.
and their core engine is a mechanism called self-attention.
Yeah, and self-attention works by evaluating the relationship between the token it's currently generating and every single previous token in the sequence.
So if a model generates, let's say, a 2,000-word essay,
Could generate word 2001, it calculates an attention score against all 2,000 prior words.
wow.
And as the sequence grows, the computational cost balloons quadratically. In computer science, we denote this as an O of L squared process, where L is the length of the text.
It's like reading a 500-page mystery novel, but every single time you turn a page, you are forced to reread the entire book from chapter 1.
Just to remind yourself what color the suspect's car was.
Exactly.
Yeah.
It is highly accurate, like you definitely won't forget the car,
Yeah.
but it is computationally agonizing.
It's just so slow.
So the Nautile-370M paper introduces an entirely different sequence operator to solve this. It's called second attention, or SCA. And the paper claims this is based on the, and I'm quoting here, derivative of a characteristic function.
Which is quite a mouthful.
It is. Let's unpack that, because throwing the phrase characteristic function around is a really quick way to lose people.
Fair enough. Let's break it down mathematically, but practically. So in probability, a characteristic function completely defines the behavior and shape of a probability distribution.
Okay.
It essentially captures everything about the data. When you take the derivative of that function, you are effectively calculating the moments of that distribution.
Well, moments.
Yeah, like the mean, the variance, the skew.
Ah, I see. So instead of storing a massive list of, say, every single footstep a runner took on a track, you're just calculating their momentum, their velocity, and trajectory at a given second.
Precisely. You capture the essence of the movement without hoarding all the raw data points.
That makes sense.
By tracking these mathematical moments, the model maintains a constantly updating, highly compressed state.
Let's bring this back to the detective novel analogy. If standard self-attention is rereading the whole book over and over, SCA is like the detective maintaining a highly organized evidence board.
I like that.
You read a chapter, you extract the clue, you pin it to the board, you just move on. When you need to remember the car color on page 500, you don't reread the book.
You just glance at the board.
Exactly. And updating that board takes the exact same amount of cognitive effort on page 5 as it does on page 500. It scales linearly. It is an O of 1 process.
Yeah, the evidence board is a really solid analogy for the speed. But usually, when a human compresses a whole book into a single board, they lose nuance.
Right, you inevitably drop minor details to save space.
Exactly. What makes SCA revolutionary is that the paper mathematically proves, specifically in their Theorem 1, that this compression is entirely lossless.
Wait, really? A mathematically perfect summary.
Yes.
How can you compress hundreds of pages of text into a single updating state and not lose a single comma?
It all relies on how the model maps the data into spectral space. To update its memory state, the model doesn't just store words like text in a database. It converts the sequence into a complex valued gradient summary.
Okay, you're losing me a bit.
Hang with me. When it needs to recall something, the current word emits a spectral query. It computes what's called a complex Hermitian inner product.
Okay, complex Hermitian inner product sounds like advanced theoretical physics. Let's ground this for a second. Complex usually refers to complex numbers, right, with real and imaginary parts.
Correct.
And spectral implies frequencies, like a radio wave or an audio spectrum.
Yes, exact.
So instead of thinking of words as text in a filing cabinet, we should be thinking of them as, like, overlapping wave frequencies.
That is a highly accurate way to visualize it. Think of constructive and destructive interference in audio waves.
Okay, I can picture that.
The Hermitian inner product is basically a way to measure how much two complex vectors or waves align with each other. The model evaluates just 2 learned spectral points per attention head.
Just two.
Just 2. And because a complex vector can jointly encode the position of a word in its phase and the meaning of the word in its magnitude, the specific wave signature of any individual token can be extracted from the combined wave perfectly.
Oh, wow. So you essentially tune the radio dial to the exact frequency of the clue you need, and the wave isolates it perfectly from the noise. It doesn't get fuzzy.
Exactly. And the authors provide a mathematical corollary proving this. They demonstrate that SCA can reproduce any output of a standard softmax attention layer as a special case.
That's incredible.
It is provably just as expressive as the massive, compute-heavy self-attention, but it operates infinitely faster for state tracking.
Okay, I have to stop you there and push back on this a bit.
Go for it.
If this complex wave function is a mathematically flawless summary, and it takes up almost zero compute overhead compared to self-attention, then the memory bottleneck is completely solved, right?
Theoretically, yes.
But I'm looking at the architecture schematic for Nautile-370M. It has 24 layers, and they are not all SCA layers.
Right. They aren't.
It uses a repeating block 2 SCA layers, followed by one old-school transformer layer. If the math proves SCA is perfect, why are they hauling around the heavy, clunky transformer architecture at all?
Because there is often a very stark difference between a continuous mathematical proof and the physical reality of a silicon chip.
Ah, okay.
In the theoretical limit, yes, the spectral integral perfectly encodes the entire document. But to actually run this on a GPU or TPU, you have to discretize the math.
Meaning you can't process an infinite wave on a computer with finite memory.
Precisely. You have to take snapshots of the wave. You have to evaluate it at finite points. They are only evaluating 2 spectral points per head.
And that causes issues.
Well, because of this approximation, a single SCA layer can struggle with operations that require intense, exact, pairwise comparisons across a vast document.
Like what kind of operations?
Think of a task like coreference resolution. If you have a 50-page legal contract, and on page 40 it says, "He shall be liable."
The model has to figure out exactly which person he refers to.
Right. SCA is phenomenal at incremental context building and understanding the general state of the contract. But for that surgical pinpoint routing of a specific pronoun to a specific name 30 pages ago?
Needs backup.
Exactly. It relies on the exact precision of a standard transformer layer.
So they use the O of 1 speed of SCA for reading the bulk of the text and keep the O of L squared transformer layers as a heavy-duty fallback for that complex cross-referencing.
Exactly. The 2-to-1 ratio makes a lot of sense as an engineering compromise.
That's really clever.
And the authors actually note they didn't even have the luxury of testing multiple layer ratios.
Well, because of the compute limit.
Yeah. When you only have a single TPU slice for 30 days, you can't run endless ablation studies. They analyzed previous hybrid architectures, placed a pragmatic bet on the 2-to-1 split, and just committed to it.
That constrained compute budget really forces some strict choices. especially regarding the training data.
Oh, absolutely.
Because if your architecture is a hybrid compromise and your compute time is incredibly limited, you can't afford to feed the model junk. You can't just scrape the entire internet and hope the AI figures it out.
No, the data curation was meticulous here. For the raw pre-training, they fed Nautile about 350 billion tokens from a data set called FineWeb Edu.
Which is mostly educational content, right?
Yeah, it provided the foundational factual knowledge, basic entities, historical facts, linguistic structure. Then they layered in 250 billion tokens of a data set called SY.
What's SYN?
It's explicitly focused on step-by-step chain-of-thought reasoning.
Oh, wow. 250 billion tokens of pure logic puzzles and step-by-step problem solving.
Yes.
That builds a massive capacity for reasoning. But there's a gap here, I think.
What do you mean?
Well, if the model only knows raw encyclopedia facts and dry logic chains, how does it learn to actually interact with you? If I ask it a question, I don't want a response that looks like a raw textbook dump.
That's a great point. They bridged that gap using highly specialized synthetic augmentation. The team generated 4 million targeted synthetic documents using a process called retrieval-guided generation.
Okay, break that down for me.
They took massive, highly capable teacher models, specifically GPT-OSS-120B and Mistral Large 3, and used them to rewrite varied instructions so they adhered to a perfect, standardized template.
Oh, it sounds like they used the giant models as etiquette coaches for the tiny model.
That's a great way to put it.
They gave the tiny model the raw knowledge, but used the massive models to write the formatting rulebook.
Oh, it is a classic distillation technique. The 371 million parameter model already possesses the latent reasoning from that SYNth dataset. But these 4 million template documents force it to present its answers cleanly, respect user instructions, and output a structured layout.
That makes total sense. Which actually brings us to, honestly, the most dramatic plot twist in the whole deep dive.
The reinforcement learning phase.
Yes. So the team has the hybrid architecture, they have the strict data diet, and they want to push the model's math capabilities even further.
Right.
To do this, they turn to reinforcement learning, attempting to boost its score on a major math benchmark called GSM-8K. They use a standard industry technique called GRPO. But instead of getting smarter, the model's reasoning actually degrades.
It's wild. It's a profound failure that reveals a lot about how we actually train these systems.
So let's decode this. GRPO, Group Relative Policy Optimization. How does that actually calculate a reward for the AI?
Well, instead of just telling the model good or bad for a single answer, GRPO asks the model to generate a whole group of different answers for the same prompt.
Okay.
Then it scores them all, calculates the average score of the group, and penalizes the answers that fall below the average.
While rewarding the ones above it.
Exactly. It's grading on a curve.
But grading on a curve makes sense in theory. So why did punishing the bad math answers destroy the model's ability to reason?
You have to remember the day diet. They force-fed this model 250 billion tokens of chain-of-thought logic.
Right.
The capacity for sound structural reasoning was hardwired into its parameters. So when Nautile-370M got a complex math problem wrong on the benchmark, it almost never meant the underlying logic was flawed.
Then why was it getting them wrong?
It usually meant the model had laid out a brilliant, multi-step logical deduction, but made a tiny factual slip-up, like a basic arithmetic error, at step 6.
Oh, I see. It's like an engineering student who writes out a flawless 3-page proof for a physics exam, but at the very end accidentally writes that 7 times 8 is 54.
Yes.
The final answer is wrong, but the logic was beautiful.
Exactly. But standard GRPO only evaluates the final output. Because the model's initial success rate on these hard math problems was around 28%, the vast majority of the group answers were failing.
So the algorithm looked at the 72% of answers that had a wrong final digit and applied a massive negative penalty to the entire chain of thought that led there.
Yes. It was punishing the model for structurally sound reasoning simply because of minor arithmetic errors. The reinforcement learning was actively dismantling the model's logical framework.
The training process was gaslighting the AI.
It really was.
It was essentially telling the model, your final number is wrong, therefore your entire capacity for deductive logic is garbage.
Exactly.
How do you even rescue a model from that without completely abandoning reinforcement learning?
Yeah, engineers implemented a really brilliant 3-stage rescue plan. Stage 1 was deploying a variant called Dr. GRPO.
Dr. GRPO.
Yeah. They used a larger LLM as a judge to evaluate the answers, but crucially, they removed the standard deviation normalization that GRPO normally uses.
Wait, Why does removing the standard deviation matter so much here?
In statistics, if you subtract the mean and divide by the standard deviation, and almost all the scores in your group are zeros, meaning failures, the mathematical penalty for being slightly below average becomes incredibly extreme.
Oh, I see.
It creates wild, volatile updates to the model's brain. Removing that normalization stabilized the learning. It didn't boost the math scores, but it stopped the wild mood swings and cleaned up the output format.
So Dr. GRPO acts like a stabilizing copy editor. What did they do for stage 2?
Stage 2 was gradient balanced GRPO. They mathematically decoupled the positive and negative rewards.
Really?
They built a firewall between the successful reasoning paths and the failed ones. This ensured that the sheer volume of negative rewards from that 72% failure rate couldn't overpower and drown out the positive signals from the 28% of times the logic succeeded.
Oh, wow. They stopped the algorithm from burying the model's successes under an avalanche of punishment.
Exactly.
That must have moved the needle.
It did raise the score, yeah, but the improvements eventually hit a ceiling. The true breakthrough, the mechanism that actually unlocked the reasoning capabilities, came in stage 3.
Which was?
On-policy self-distillation.
Self-distillation, meaning the model distilling knowledge from itself. Walk us through the mechanics of that.
It's an incredibly elegant approach. They simply let Nautile-370M generate its own answers to thousands of complex problems.
Okay.
They evaluated the final outputs, discarded every single incorrect answer, and kept only the perfectly correct reasoning traces.
Yeah.
Then they fine-tuned the model entirely on its own verified successes.
It's generating its own study guide.
That's exactly what it's doing.
It takes a test, throws away all its mistakes, and intensely studies the moments where it was brilliant.
Furthermore, they used an unnormalized advantage score. This meant that if the model solved a problem it usually failed at, the reward was massive.
And if it solved an easy problem.
The reward was tiny. It essentially created an automated, built-in curriculum that constantly pushed the model to focus on the hardest logical leaps, with zero human intervention required.
It just bootstrapped its own intelligence.
It did.
And looking at the results, the strategy undeniably worked. The final GSM-8K reasoning score hit 33.4%.
Which is huge.
Just for context on why that matters to you.
Yeah.
A competing model like Quen 2.5 0.5b scored 28.3%, and Smolem 370M scored a dismal 7.4%.
Right.
And Nautile achieved its 33.4% after training on a total of just 0.8 trillion tokens. Those competing models trained on up to 28 trillion tokens. It is doing way more with a fraction of the data.
The efficiency really validates the entire pipeline, the hybrid spectral memory, the strict data constraints, and the realization that standard reinforcement learning can be destructive if not carefully managed.
But understanding how it was built naturally leads to the question of application.
Of course.
I want to ground this for you listening.
Hmm.
If you download Nautile-370M, what are you actually using it for? It's hyperlogical, but it's tiny. I assume I'm not asking it to code a mobile app or write a screenplay.
No, the researchers are very transparent about the boundaries. They intentionally stripped coding data out of the training corpus.
Oh, really?
Yeah, when you only have 371 million parameters, you cannot afford to waste parameter space trying to teach the model Python syntax.
Makes sense.
It's also not designed for long conversational chats. Maintaining a consistent, nuanced persona over a 20-turn dialogue requires billions of parameters to hold the subtle context.
So if it can't code and it can't hold a long conversation, where does this hyper-efficient reasoning engine actually shine?
It excels in environments where precision, logic, and speed matter way more than creative fluency. So edge computing, precise text classification, deep sentiment analysis, and complex intent detection.
Okay.
But the paper proposes one incredibly fascinating use case: synthetic population studies.
Synthetic population studies, like
Yeah.
running a simulation of a whole population.
Yes. Because Nautile-370M uses second attention, its memory footprint is a flat O of 1. It takes up almost no VRAM.
Oh, wow.
This means a researcher can spin up 10,000 instances of this model simultaneously on very cheap hardware. You can assign each instance a slightly different persona, background constraint, or demographic profile.
And suddenly you have a massive simulated populace that can react to a new policy proposal or a product launch.
Exactly. Running 10,000 simultaneous instances of a massive model like Claude or GPT-4 would be financially ruinous, but with Nautile, it is cheap and incredibly fast.
So instead of querying one massive omniscient brain, you simulate a town of 10,000 highly logical citizens and watch how they interact with information.
It changes the paradigm entirely.
It's a total shift from the monolithic oracle to a swarm of deployable reasoning engines.
It really demonstrates that utility isn't just about how much a single model knows, but how flexibly and efficiently you can deploy its logic.
Let's bring this all into focus. We started by looking at the massive bottleneck in modern AI, that O of L squared jigsaw puzzle of standard attention.
Right.
And Nautile-370M solved that by rethinking the fundamentals of memory, translating documents into a lossless spectral wave using the 001 speed of second attention.
While keeping just enough transformer architecture for precision.
Exactly. They proved that world-class engineering isn't about having the biggest compute budget. It's about understanding your constraints.
They meticulously curated their data diet.
And when standard reinforcement learning threatened to destroy the model's logic, they innovated. They realized that letting a model learn from its own verified successes through self-distillation was the real key to unlocking its potential.
The paper serves as a powerful reminder that in computer science, strict constraints are often the greatest catalyst for creativity.
Being truly well-informed about the future of this technology means looking past the headlines about trillion-parameter data centers. The most profound leaps are happening right here at the structural level. It's about turning a sprawling infinite memory problem into a clean, mathematical evidence board.
Well said.
Before we wrap up, there's one final lingering thought I want you to mull over. We saw during that self-distillation phase that Nautile had achieved its most profound leaps in logical capability, not by reading more human-generated text, but simply by generating its own answers, discarding the failures, and intensely studying its own verified successes.
Yeah, learning from its own internal monologue.
Exactly. So at what point in the evolution of this technology does an AI's own carefully curated internal logic become a more valuable source of training data than the entire messy, contradictory history of the human internet? Keep diving deep.